It is very difficult to write a single piece of code to identify mountains because mountains can take different shapes and forms and colors, right? Mountains can be brown, mountains can be green, mountains can be um, it can be white. If you go to a snow side area, it can be white. So there can be different ways how mountains can look like. Mountains can take different shapes. So elephant still was something we could potentially do. But the moment you relate it to more complex objects, they become increasingly more and more difficult. So it is very difficult to classify and write code for mountains. If I want to identify mountains, I cannot write the rules. There's no way I can write a single set of rules to identify mountains. And if you think about it, the same also applies for other forms of unstructured data. So next time you go to a Google Assistant, and it's not new. Obviously, now the assistant has been named to Gemini. But if you go years back, Google started with that microphone button years back, long time back. It's not even like long time back, even before OpenAI existed as a company. So Google had that microphone button, right? You can say, okay, Google, and it will do things for you. What is it? What is that doing? Every time you use that particular phrase, or every time you say, okay, Google, your microphone will actually fire up. Every time you say, okay, Google, a series of things will start happening. Every time you say, okay, Google, a series of things will start happening. So first, Google has to recognize it is you who is talking. And imagine how complex that would be. Imagine how difficult it would be to do that. It would be very difficult to recognize that it is exactly you who is talking. So recognizing that would be very difficult to do. You cannot write a set of rules. You cannot say, okay, if this, then it is Cheyenne. If this, it is not Cheyenne. If this, it is Roshan, else it is not Roshan. It's very difficult, and it is very difficult to hard code audio data into specific words, because every time I say something, the manner in which I say it will be different. Every time you say something, there is a very unique way that you will say it, right? Because even audio data, whatever you say, your speech can be encoded in numbers. So every time you say something, you are using a different pitch, a different frequency, a different voice modulation, a different tone. So the tone is very different, and it's very hard to write rules in these kinds of cases, right? I hope everybody at this point in time understands that there are many applications we see in the real world today which are simple circuits, which are simple rules, simple if then else instructions. At the same time, there are many applications we have today where writing these simple rules are not only difficult, but they are impossible. You cannot even fathom what these rules potentially could be. We don't know what these rules will be. And that is what led to the growth of machine learning based AI. So here also we are designing intelligent machines. Here also we are designing intelligent systems. We are making machines intelligent, but not using static rules, using machine learning. So when the rules are hard, what do? We give the machine lots and lots of data. We give the machine lots and lots of data, which are nothing but input output combinations. Okay, we give the machine lots and lots of data, and we let the machine figure out the rules. We do not hard code the rules ourselves manually. We don't hard code the rules manually ourselves, but we let the machine figure out the rules instead. And that is what is referred to as machine learning. And as you can see, it is more dynamic, unlike rule-based intelligence, which was static because we are pre-programming, we're writing the code, right? It's static. Machine learning is dynamic because the rules are learned by the machine, and it is also much more prone to mistakes. So unlike static rule-based intelligence, if you see in machine learning, it's more dynamic, and it is also error prone. It's prone to more mistakes and it's prone to more errors because it can happen that the machine ends up learning the wrong set of rules. To help you understand this idea a little better, you can think of a very simple analogy of how a kid learns, of how humans learn. Humans also learn from lots and lots of examples, right? If you think of a typical human being, human beings also learn from lots and lots of examples. So machines also learn from lots and lots of data or lots and lots of examples. So give the machine lots and lots of data, input output combinations. Teach the machine just like how you teach a small kid that, hey, okay, if this is the input, this is the output. If this is the input, this is the output. Just teach the machine the same way that you will teach a small kid. So if the input is this, the output is this. The input is this, the output is this. The input is this, the output is this. Give lots and lots of these input output combinations. And based on that, the machine will use some algorithm. It will build a mathematical model. And then using that mathematical model, it will do the predictions. So this diagram gives a very, very basic picture in terms of how machine learning actually happens in the real world. So you can see here that we are not giving any static rules. We are not hard coding the rules. Rather, we are giving the machine lots and lots of input output combinations. So we are giving the machine lots and lots of XY combinations, XY, XY, XY. You can see 1, comma 2, 3, comma 4, 5, comma 6, 7, comma 8. So we are giving the machine lots and lots of these so-called input output combinations. And this is called the training data. So what is this entire thing called? This entire thing is called the training data. So the machine is getting trained on the training data. Okay. So you have the training data, the data that is having the input output combinations 1, 2, 3, 4, 5, 6, 7, 8. You have the training data. And we will use some algorithm. And based on that algorithm, we will build a mathematical model. The mathematical model is nothing but the rules of the function. So, and the rules of the function that we are learning right now is y equal to x plus 1. So this is the rules and the function that we have. So based on the data xy combinations, we use some algorithm, and based on that algorithm, we learn the model. And the model that we end up learning here is y equal to x plus 1. That is learned. Okay, so this is the biggest difference between the classic rule-based AI that I explained so far and machine learning, because in machine learning, what is happening is this equation is learned. This equation is not something that we are providing initially, but this equation is something that the machine is learning from the historical data. So based on whatever patterns I'm showing it, based on whatever initial data patterns I'm showing it, the machine is able to figure out this relationship. The machine is able to figure out this association between the x and the y. It is able to figure it out. It is able to figure out the association between the input and the output. And once it understands the association, so based on the data, using the algorithm, once it figures out the association, once it builds the model or the rules, once it figures it out, that is called model fit. That process, that part of the process is what we call training, model training, or fitting a model. So oftentimes in machine learning, as we go through the remaining discussions, we will oftentimes use a term called model training or fitting a model. So what is the meaning of fitting a model? What do you mean by model fit? This is what is model fit. Okay, you have the data, you will use some algorithm, and you will train the model, or you will fit the model. And the next part is, once you have learned the equation, once you have learned the rules, using that you will do a prediction. That is what we call model.predict. So there are two parts to the equation. The first part is we use the data and we do a fit. We create an equation. And the second part is based on the equation, we do a dot predict and get the predicted value. So these are the two parts of the equation that we have here. Now, to summarize it further, this is how it looks like. And as we go through the remainder of our discussions, we will actually see in hands-on how this can be done. So how we can use different types of data, and how we can use different types of algorithms, and how we can actually build different models. Okay, how we can basically have the machine learn the rules. And that is the biggest advantage, because real world data is so complex, even for seemingly unstructured forms of data. If you look at images and audio, video, text, especially the examples I was taking, they are so difficult that it is very hard to write the rules. So just give the machine lots of examples and let the machine figure out those rules. Let the machine figure out what the associations will be. And that is the biggest benefit of machine learning. But as you can imagine, sometimes the machines will not do the right job. Sometimes the machine will not learn the rules properly, and whenever the machine makes those mistakes, we get errors. Okay, so that is a part and parcel of machine learning that we have to accept. Okay, so sometimes we have to accept that machines will make a mistakes, machines will do a poor job. And when that happens, whenever the machines do a poor job, whenever the machines make a mistake, we have to accept that that is when we have to we have to accept that that is when we see mistakes happening. So sometimes you will see a picture is not classified correctly. Sometimes you in the voice assistant you will say something, but the model will hear something else, and that is the same reason why when you type something, sometimes wrong responses come. Okay, because the rules are not correctly learned. So another very nice way to think of machine learning would be this example. This is the example I typically like to take so that you can connect the dots better. And as I said, one of the best ways to think of machine learning is how a human learns, how a kid learns. Okay, so how does a human being learn? How does a kid learn in kindergarten? So, okay, so let's say it's your first day in school, it's your first day in kindergarten. How do you learn? How do you study something? How do you figure out something? Okay, so somebody has to teach you, right? Somebody has to teach you what is an apple, what is a banana, what is a watermelon. Somebody has to show you lots and lots of example data, and somebody has to teach you that okay, pictures like this are mango, pictures like this are banana, pictures like this are watermelon, and so on and so forth. So somebody has to give you the data, and somebody has to explicitly teach you that okay, I show you a fruit. So that is what you do to a kid also, right? You show the kid examples of fruits. You show them and you tell them, okay, these are what we call apples. This is the input and this is the output. You show them another fruit and you say, okay, you know what? This is a fruit, how it looks like. So you see the size of the fruit, the shape of the fruit, the color of the fruit. All these are the inputs, right? So you're showing the fruit and you're telling the kid, okay, this is the fruit I'm showing you right now. You please observe the fruit carefully, observe its attributes, and then you're telling, okay, this is called a guava. This is the output. So see how humans learn, how young kids learn, they learn the same way. So, okay, otherwise, if you don't teach the kid properly, the kid has no way of knowing that this is an apple or this is a guava. So now you're showing lots and lots of examples to the kid. You're giving lots and lots of examples. You're showing the picture of the fruit and you're telling it what the fruit is called. You're showing the picture of the fruit and you're telling what the fruit is called. And it is through those examples that now the kid understands that, okay, this is actually called a guava. And that's the core and that's the crux of what we are trying to do in machine learning. Okay, the machine is learning, or in this case, the kid is learning from the historical data. And once it learns the patterns, once you have taught it well, once you have taught it, apples and guavas, now it has a model. And now if you show it a new kind of fruit, the kid will know what that fruit is called. Okay, so if you show it a new kind of fruit, the kid will be able to predict between those two varieties what it is called. Remember, it will only be able to predict from the two varieties. It cannot estimate some other kind of fruit. Let's say you haven't taught it some other fruit like a watermelon. The kid will not know what a watermelon is because you have never taught it. Okay, so the kid's knowledge or the kid's model is only limited to what you have taught it, only limited to the training data. And that is why in machine learning, as we get deeper into building models and other things, we will discuss this topic in detail. That it's very important in machine learning that we decide, that we figure out what is the overall uh, what is the overall quality of the data. The quality will dictate a lot of things. Okay, so having the right data quality is very, very important. Okay, so having the right data quality is very, very important in the larger scheme of things. Okay, because if your data is not right, if you're not training the kid properly with the right data, the model that ends up getting built is also not right. Okay, and just to show you, just to give you a couple of examples, with respect to this particular thought, there have been some very interesting mistakes that machine learning has done, right? So there have been some very, very interesting, mistakes that machine learning has done over the years. And one of these mistakes I wanted to share with you was this one, where Google actually misclassified a black person to be a gorilla. This was long back. This was in 2015. Okay, but it was a blunder that Google made. So what happened was, this is how the story goes. There was a person named Jackie Alsine, and he took a selfie with his friend, and Google and they used the Google Lens to see the picture. And what happened was the Photos app, because Photos was very new around that time. Today, Google Photos is very good. This was 10 years back, and the Google Photos app mistakenly labeled a black couple as gorillas. Now, if you think about it, this is classification, right? It's classification. But if you think about it, what went wrong? What actually went wrong? What went wrong was because the data was wrongly labeled. Okay, so the original model, because Photos was a very new application that time in Google's repository. So whatever data they used to train the model was incorrect. Okay, so otherwise it does a lot of things right. But if you see, these are all the pictures that they took, right? And all of them were labeled as gorillas. So later when they, when they went and went to the photos application, just like you use photos.google, and they search for gorillas, they found their pictures. This is model prediction happening. So what you are seeing right now is uh, this is like model prediction happening, because that's how in a way the data was trained. And if you think about it very clearly, even Google kind of acknowledge the sensitivity, and they say genuinely sorry and there's a lot of work to be done, all that. And you can see we are taking immediate action to prevent this type of result from appearing. And what is the action they have taken? And this action exists even today, right? This action exists even today. If you go to the Google gorillas application, sorry, if you go to the Google application and if you type gorilla, okay, if you search for the gorilla keyword, the gorilla keyword actually doesn't appear, so it was such a sensitive mistake that even today, if I go to my Google photos and if I search gorilla, you can see gorilla doesn't appear. Okay, because I mean, Google doesn't want to risk it again. They don't want another black person to be misclassified as a gorilla. And if you think about it conceptually, what is really going on, based on some of the foundations that we covered until now, conceptually we have some X and we have some Y. As I told you, machine learning is that form of intelligence where the data has to be trained, the model has to be trained. You have to show it lots of input output combinations. So input is like the picture, input is like the original image, right? And output is like the label. What is the label? What is the class? What is it actually called? So we are looking at lots of these XY combinations. And one of the problems that happened in this application was there were lots of labels of gorillas, right? And it turned out that the pictures were all black, which is how it's supposed to be, because gorillas are supposed to be black, right? So a lot of label data was used to train the machine, the same way how you teach a small kid. The same example I told you a while back, right? You're teaching a kid with lots of examples of fruits. So the same way, it's almost as if you're teaching the kid with lots of examples of gorillas. You're showing it a picture of a gorilla and you're saying, hey, you know what is called a gorilla? Another picture, it's called a gorilla. Another picture is called a gorilla. Another picture is called a gorilla. Turns out there were also labels for human beings, right? Now, who is a human being? What were the kind of photos that were shown as a human? Okay, you're showing pictures of humans. You're saying, hey, this is a human, this is a human, this is a human, this is a human. That's how the machine is learning. The problem was whenever you showed pictures of humans, they were almost always white, because that is how things were in the early days of machine learning. There was a lot of biased systems that we had because the data around us were also biased. I mean, even today, if you search for the term human in Google, you'll find actually a lot of the search results, maybe 80% of your search results that are returned are white people. So even when you're teaching the small kid, the kid is picking up the color parameter. The kid is somehow mistakenly picking up that, okay, whenever I see something black, it's a gorilla. And whenever I see something white, it's actually a human. So the kid is mistakenly picking up that pattern. And that is what is going on in the model training. Okay, XY patterns, use an algorithm, build a model. So the model is built. So this is what Google Photos would have done behind the scenes. They have built a model. This would have taken a long time, a lot of processing and all that it would have taken to do that, right? Because these are like millions and millions of pictures they would have labeled to get this model. And now when you upload a photo, when you go to, you click a photo with your smartphone and you upload to Google Photos, what it's doing is it's simply doing prediction, right? So you have the existing data and you build a model, you train a model. This is the trained model that Google Photos is having right now. And next time, you are in the Photos application now, right? So now you have a trained model. So whatever model you train, this is the trained model that you have. This is nothing but the XY relationship, the rules, right? And now next time I give you a new photo, next time I upload a new photo on Google, the model will simply do model.predict. Okay, we will simply do model.predict, and we will try to predict that based on what rules I have learned, what is the predicted value of y predicted. So this is what is actually going on behind the scenes in Google Photos and a lot of other applications. So initially some data was used to train a model, and then later on, given some new data, you're constantly trying to make a prediction. What is the result? Is it this? Is it that? So that is what is going on behind the scenes. And I know this is the gorillas example I took, but I hope you can relate to it. And this example was again to kind of really kind of help you understand that what is actually going on behind the scenes, and why some of these systems can often make very, very sensitive mistakes. But not quite. I mean, it does a pretty decent job. I was talking about elephants, and if I go to my Google Photos and show you pictures of elephants, it does a nice job. It does a nice job to show elephants correctly. You can see my Google Photos right now, and you can see that there are some wonderful pictures of elephants we are able to see. Okay, this is not rule based, mind you. It is not as if Google has defined a series of hard coded rules saying, okay, you know what, pictures like this are elephants and pictures like this are not elephants. No, it is not a set of rules, but this is also learned using machine learning. Okay, so and another one fascinating, mountains, right? Mountains are very hard to very, very difficult to kind of predict, and it's very hard to write rules explicitly for mountains. And if you see, even for mountains, we will actually see some excellent examples coming up for mountains. So you can go and this is my Google Photos once again. You can see. So these are examples of mountains, and it's very hard to write rules and very difficult. I mean, for example, look at this picture. I took this picture from the flight, right? I mean, I don't know. It's very hard to spot mountains, but actually there are mountains. I know for a fact there's some mountains. There's some mountain ranges you can see at the backdrop, but I mean, it doesn't look like a typical mountain. I mean, this is very clearly it's a mountain. This is very clearly it's a mountain, but look at this one. It's very hard to define rules for mountains, right? Very difficult. Like mountains can be like this typical triangular shape, or mountains may not be triangular. It is not guaranteed, or mountains can be like this, or mountains can just be like this, no? So there's a very clear triangle that is forming, but here there is no triangle that is forming. This was a flight I took when I was going to Ladakh actually, just some time back, and you can see again it's very, very difficult to write rules around mountains. Very hard. Okay, and these are some fascinating examples that that machine learning can help you solve, which you cannot solve using static rules. Okay, so I hope part of this conversation, everybody in the audience is able to relate how powerful machine learning can be. But oftentimes you will still see some one-off mistakes will continue to happen. Even in my photos, there are one-off mistakes that will continue to happen. A very common one will be, let's say, snow versus cloud. Very common one. I mean, if you search for snow, there might be some instances where clouds are coming, because clouds and snow are look the same. I mean, especially if you're in a flight and if you're looking at taking a photo picture of a cloud from flight, it looks very much like snowfall. No, I mean, if you go to a mountain range and you click a picture, it's very similar. So oftentimes those kinds of mistakes will happen, but the idea is to make the models better. And this is again a cornerstone of machine learning. You start by building a base model. You start by taking some input output data and training the model, and the most important part in machine learning is to continue to retrain the model. So initially you build a baseline model, a basic model you build, and next what you do is you try to make it better. You retrain the model, make it better. Take the fresh data, retrain the model, make it better. Take fresh data, retrain the model, make it better. So how do you continue taking more and more data, and how do you keep continue making the models better and better and better? So that's the whole idea of what we do in in machine learning.